So Anirudhan, I have a AAA battery here. So is that potential difference that you mentioned something similar to the potential difference I have across this?
Yes, absolutely. So if you see this, you are doing energy, you are giving energy to take it from position 1 to position 2.
Correct.
So there is some energy associated with positions 1 and 2. Similarly, there is energy stored inside the battery.
Okay.
In electrochemical form. So that is potential energy. It is not being used. When you just keep it as a battery, it's not being used.
It's available there.
It is available, but nobody is using it so far. So the way to represent a battery is like this.
Okay.
This is the electrical symbol.
So this will be the symbol we will keep on using.
We are going to keep using the symbol. You are going to keep seeing this again and again and again in this course. In fact, in future courses.
So the lengthier one indicates positive side.
This is the positive side. The lengthier one indicates the positive side. The smaller side indicates the negative side. So in other words, it is like points 1 and 2. Right? Okay. So in the previous page, we had point 1 and 2. So you imagine somebody has already taken a charge from separated charge between points 1 and 2. There is ability for the charge to come back.
Okay.
Right? So there is potential energy that can be used. And we say that the potential difference between the two terminals of the battery is that V.
Okay.
That the voltage that we have been talking about.
So I have been touching like this, no?
Yes.
I feel no difference. But I was also trying connecting a wire in between. And it was getting hot.
What happened? Yes, you felt it?
Yeah.
You are not able to hold it for a long time, right?
No.
Yes, that's
what
right.
What could be the reason?
So, if you look at this battery, it has stored energy.
Correct.
But you need flow of charge for you to be able to use that energy.
Okay.
Because if you don't allow charge to flow, it will still be in the form of potential.
Okay.
So, we'll go back to our earlier analogy. So, you had the ground and you had a mass at point 1, right? If you just hold it at one point, it will just remain there. It will just remain there, right? It has potential. So, imagine you have a shelf, right? I'll call this, I have taken it from one shelf to another shelf. I have taken this mass M and I have moved it from one shelf to another shelf. It is just sitting there.
Correct.
It is not doing anything.
Yeah.
You can imagine this battery to be like that. Until you remove that shelf and allow it to move, right? You cannot use that energy. Same way, to use this energy, you need to allow the charges to move. And remember, charges always get conserved. You cannot destroy or create charge.
Okay.
Right?
Correct.
So, charges move in some kind of a loop, right? So, you need to create some kind of closed loop. Now, we are going to discuss that a little bit later,
sure,
right? But now, maybe we'll look at this battery by itself.
Yes.
And you asked an interesting question, right? You said if I put a wire, it becomes hot.
Yeah.
And if I put, your hand, your 2 fingers,
I feel no difference.
You feel nothing. Let us see what will happen. So, let us complete this,
please,
with another very simple component that we have seen. So, I am going to take this same battery V, we will assume it is V, and I am going to complete it using a resistor. I think Janakiraman mentioned something called a resistor, right?
Yeah, actually we did a heater experiment.
Yes.
So, resistor kind of
was covered.
Yes.
So, that should answer your question, why the wire is getting hot. You mentioned the word heater.
Okay.
Right? So, in the heater, you must have used a resistance R inside it. True. So, there is a resistance of the wire that you are connecting or the finger that you are connecting. So, you are closing this with something which has some resistance. Now, what is a resistance? I think you know from Ohm's law that you have a relationship between the voltage and the current.
Sure.
But now what is current? We need to look at that as well.
True.
Right? So now let us figure out what current is before coming back to this.
Yes.
Because unless we know each and everything.
Then it will become clearer, I guess. Yeah.
Correct. So now, so far we have seen, like I said, the mass is kept on a shelf. There is no ability for the mass to move. The battery is just sitting by itself. There is no ability for charges to move.
Yeah.
If you imagine that I'll go back to my old electric field, similar to this electric field situation. I have a uniform electric field, and I imagine that from points between points 2 and 1, charges can move. I am in vacuum. So I take a charge, I place it in an electric field,
It will
move. Now imagine I don't just take one charge. I have something that can supply. I am going to draw a funnel like this. I have charges. I am going to show it as positive charge.
Okay.
I have lots of
So
charges.
it will be keep on.
Correct. I have a funnel that is delivering charge.
Okay.
Right? What will happen? That charge will start moving. Okay. You have an electric field. You have a charge. It experiences a force.
So all the time there is some charge.
There is some charge constantly flowing from one side to the other.
Okay.
Okay. Now what I am going to do? I am going to take a snapshot at some intermediate place. I am going to take a snapshot.
Okay.
I am going to figure out how much charge. So what I am going to do? I am going to observe it. I am going to keep seeing it for some time t, let us say.
Okay.
Okay. And I am going to see how much charge has actually
Past that line
and I will say
over
that
the time t.
over time t, and I will say that charge is q.
Okay.
Okay. I can wait for long enough time. It doesn't matter whether I take a small amount of time or large amount of time. I am going to take some time t and observe the charge q. Now, the average current, or rather the current, is defined as the amount of charge that has traveled over a period of time t. So you take the ratio of these two quantities, it gives you the rate of flow of charge. That is nothing but current. Okay. So this is q by t, this is rate of flow of charge. So in fact, the simplest definition of current is rate of flow of charge. So automatically we have now changed. You can see the first situation we looked at was fixed charge. We thought of an electrostatic case. No moving charges, nothing.
Yes.
Now suddenly charges have started moving.
Yes.
Okay. So this is rate of flow of charge. Now you imagine I can make t smaller, larger.
Yeah.
Suppose I take a very, very small t, I can track the current very closely. So I can say I is delta q by delta t. If I choose a very, very small, I'll use small q to keep symbols different.
Okay.
Because I'm talking about very small charge.
So delta t
q
is a small time interval.
Very small time interval.
Okay.
And you have studied limits in high school, right?
Little bit.
Little bit. If I set the look at the limit of this as delta t goes to 0, what will I get?
It will be.
So if I set delta to be smaller and smaller, in the end, this current as a function of time will converge to the derivative of the charge with respect to time. So that is the most precise definition of current, which is dq by dt. So at every instant of time, I can calculate dq by dt, the derivative of charge with respect to time, the flow of charge with respect of time is the current. Now we have a good place, good analytical
way to say what is current.
Way to say what current is.
Okay.
Okay. So now we know everything. So now we have we know V, we know I. We have good definitions. I think you had one definition of R, but let us come to that.
Yes.
So now, what is R? R stands for resistance. Now this name has been chosen very carefully because
it resists something.
Yes. What do you think it resists?
Resists the current flow?
It resists current flow. So if you choose an element that has high resistance, if you choose a large resistor, it resists the flow of current more than a small resistor.
Okay.
Now this completely depends on the material.
Like my hand.
Yes,
Maybe it is providing high resistance.
perfectly correct.
Okay.
Perfectly correct. You can think of two cases. So one is, so this is a large resistance and this is a small resistance. We can think of two cases.
Okay.
So I'll take the same battery in both cases. Now, interestingly enough, the current will be different in the two cases. And the power will also be different in the two cases.
Yes, yes.
I think you studied the expression for electrical power last time,
Yeah.
right? So I'll call this maybe R1
Yeah.
and R2. The small resistance is R2. And this current I'll call it I1 and I2. And in that case, you use the same battery, I hope.
Yeah.
So I will just call it V.
Yes.
The voltage is the same.
Yes.
By the way, how much is the voltage here for this?
This is a AAA 1.5 watt.
1.5. Are you sure?
Yes, we can.
Why don't we check it?
We can check.
Why don't we check it?
I hope it is not a discharged battery.
We'll discuss that as well in a future class.
Yeah, correct. Yeah,
Perfect.
1.5.
It is showing 1.5 volts. Perfect. So you take this battery, 1.5 volt battery,
Yeah.
and you said you connected your hand and a wire.
Yeah.
So now I told you, depending on the material, you can have small resistance, large resistance.
Correct.
So now we have the concept of low resistance materials, high resistance materials. So you have and high resistance.
Or the other way.
Or I can do, oh yeah, it's better. So because I'm using this,
Yeah.
perfect. So I'll change it. Because I'm using large R1 here, correct. That is the right way. Low resistance. Let's start with this because this seems like it.
So what I connected was some copper wire.
Copper wire.
Maybe it provided low resistance.
Yes, of course. Copper. What else? Any other metals you can think of?
Gold.
Ah. I like gold a lot. Who doesn't like gold, right? Okay. Gold, aluminium,
Yeah. Silver. And so on.
and so on. Most metals, in fact, are very good conductors. So low resistance. What about high resistance? Do you think you can give examples of high resistance materials?
Maybe glass.
Very good. Yes.
Dry wood.
Dry wood.
Rubber.
Rubber. Yes. In fact, there are lots of materials like this,
Yes,
which
yeah.
will help. Leather,
Correct.
right? People suggest that you wear rubber shoes, leather shoes before you handle electrical equipment and so on. Now, it's interestingly, we are talking about the two extremes. It turns out that
there is something in between.
there is something in between, very important for electronics. So, these are called bad conductors of electricity. These are called good conductors. And by the way, we are talking about resistance R.
Correct.
We will also learn about something called conductance, which is inversely related to resistance.
Sure.
We'll study about that but I just wanted to kind of throw it in there.
Yes.
So now these are bad conductors. These are good conductors. Good conductors have low resistance. Bad conductors have high resistance. Now there are some materials, specially built materials, which have conductance or which have resistance somewhere in between the two.
Somewhere semi.
Semi. So what do you think they're called?
Semiconductors.
Semiconductors. Perfect. So they are called semiconductors. very important for electronics. We will learn more about them. But let us come back to it, because
Yes.
I want to come back to your
Why the wire was getting
why
hot.
the wire was getting hot, or let us go and see. So now let me take the case where you use the copper wire.
Yeah.
Let us start with that. So I am going to take my battery. It has some voltage V, which is 1.5 volts. By the way, we didn't discuss this, but the unit of potential difference is volts,
Yes.
right?
Yes,
We didn't
yes.
explicitly say
Yes.
this. So by the way, another word for potential difference is voltage.
Mm. Mm-hmm.
And the unit is volt.
Yes.
Similarly, the unit for current happens to be ampere.
Ampere.
So all of these are named after very famous physicists who did a lot of important work on electricity, magnetism,
Yes.
and so
Yes.
on. And the symbol is V for voltage and A for current, for ampere. Now we talked about materials having low resistance, high resistance. We are connecting a low resistance or a high resistance across the voltage. We will take the first one,
Yeah.
which is connecting a low resistance. I think we called that low resistance was R2. So we will connect R2 here. Now resistors have a very interesting property.
Mm-hmm.
We talked about something called Ohm's law.
Yes.
So Ohm's law
Mm-hmm.
says that if I take a resistor R, in fact in this case R2, the relationship between the voltage, in fact I'll just call it R maybe to keep it abstract, the relationship between the voltage and the current through the resistor and the voltage across the resistor is linear.
Mm-hmm. Okay.
Okay. So
Also, using this, I can find what's the current flowing
using
through.
this you can find what the current flowing through is. So now we can find out what I2 is,
Okay.
because I am applying a potential difference V across R2. So now I can find out what I2 is. So it turns out that I2 is nothing but the potential difference across R2, which is V. So this is V
R2.
by R2. Now, what do you think will happen if you put a copper wire where R2 is very small?
Current will be large.
Current will be large.
Mm-hmm.
And what was the expression for power?
I square R or something.
I square R.
Mm-hmm.
Okay. But R is very small, I is very large.
You're squaring I.
You are squaring I.
Okay.
Right? So you expect this to be very, very large.
Mm-hmm.
So that is why it's getting heated up. So you're actually burning power, dissipating power from the battery into heat. So you're converting electrochemical energy into heat energy.
And
So-
for the case of hand,
in the case of the hand,
the current is too small.
the current is too small. So in the case of, if I take the second case, actually the first case which we discussed, but the second case we are analyzing, the resistance is R1, which is very large. The current is I1. So we'll use the same relationship. I1 is V by R1. R1 was large. This is very small. And like you pointed out, you're doing I squared times R,
Yeah.
right? So the power is I squared times R. So in this case, the power dissipated is large. In this case, it is I1 squared times
Now
R.
suppose if I had to increase the current?
Yes.
Is there a way?
Yes, of course. Maybe you can suggest some ways.
I can have a different battery, or actually I have one more battery.
Oh, nice. Okay. Okay. So, as you pointed out, if you want to, do you want to increase the current in this situation with large R1? Let us try that.
Yeah.
Please don't try this experiment at home. We should inform the students.
Sure.
Because we don't want them to
Yeah.
put their finger around large voltage. But let us say we want to increase this current.
We are just taking some easy example.
We are just taking some easy example. So, we want, we want larger current. So, the only way to do it, assuming that you are using the same finger, the only way to do it is increase V.
Okay.
Now, which means increase the potential difference.
Yeah.
Now, you suggested using a second battery.
But how will I connect?
How will you connect them? How will you?
I'll connect them like this.
Okay.
Parallel?
Try it out. Try it out. You think it will? Are you able to feel anything?
No.
Most likely not.
Yeah.
Right. So, in fact, connecting them like this.
Both have same voltage.
Both have the same voltage. Correct. So, you are suggesting connecting them like this.
So, the voltage remains same.
The voltage remains the same. Correct. So, the potential difference between these two. So, you are taking two batteries. Both of them have the same potential difference across the terminals, and you are connecting them in these 2 points.
We'll try the other option, connecting them in series.
So the other option is connecting them in series. So that, we'll see what that does. I'm going to show that pictorially here. So let us see.
Let's see whether it's...
you want me to help you?
Maybe one... Yeah.
Yeah, I'll hold this one.
Is it really increasing?
Of course.
3 volts.
3 volts.
Yeah.
Of course. So, what do you think will happen here? So, I have drawn that pictorially here.
So, actually we are 2V now.
You have 2V now because you have a potential difference between the terminals of the first battery and the second battery. So, it is like, if I had to show this, it is like, so you have an electric field. Now, you have 3 points.
Mm-hmm.
So, you have point 3, 2 and 1.
Okay.
There is a potential difference between these 2 points. There is a potential difference between these 2 points. So, if you go from 1 to 3, there is twice the potential difference.
Sure. Mm-hmm.
It is like that. So, here between these 2 points, the potential difference is 2V. It is like having a third point.
So, naturally the current will be double.
Naturally, the current will be double.
Still it is small enough to
Still
feel
it
a
is small
shock.
enough. Yes. Still
Anyway, the objective is not to feel a shock, but
the objective is not to feel a shock, but
yeah.
by connecting sources in series. So, first of all, this is called a parallel connection and this is called a series connection. And parallel or shunt, these are the 2 words electrical engineers use. So, a series connection of batteries can help you get more voltage.
And at some point I will feel.
At some point you will feel. If you use enough number of batteries in series, you will start feeling it.
I'll stop with 2 batteries.
Yes, I think so.
Yeah.